Okay, continuing on with number 7, I have a single loop circuit that has a 7.2 ohm resistor, a 12 Henry inductor, and a 3.2 microfarad capacitor. Initially, the capacitor is 6.2 microcoulombs and the current is 0. Calculate the charging capacitor in complete cycles later for n equal 5, 10, and 100. Okay, so first of all, we're dealing with a circuit that has a capacitor, an inductor, and a resistor. It looks like this. There's no battery, but at the very beginning, I have this capacitor charged with 6.2 microcoulombs. Now, as we know, if we think about the energy in this capacitor, or in particular, let's look at the charge on this capacitor. Right, it's going to start out big, and then it'll oscillate back and forth, just like we had with our LC circuit, where the energy oscillates back and forth between the inductor and the capacitor. But because of this resistor element, I'm going to get a dampened oscillation like this. So gradually it'll go away. Now, there are two functions that describe this charge. Q is a function of t, or rather, the function that describes the charge has two components. It's equal to my Q max. That's going to be my 6.2 microcoulombs times the exponential, which is e to the minus RT over 2L. This will be on your equation sheet, times the cosine of omega prime t. So what I want to know is what is the charge at particular times. Now, if I think about this, the charge, if I think about the period of this oscillation, because I'm looking for the period at these particular intervals, 5 periods, 10 periods, and 100 periods, that's going to occur. This is my 0th. One period is this time. So what I'm looking for is 5 times that time. So first I need to figure out what is that time, first of all, and then I can determine the times. But I also can realize that this term, which defines how this function oscillates back and forth, then I can just get rid of that, because at those times, at 5, 10, and 100 times the period of this cyclical function, that cosine term is always going to equal 1, because I'm always going to be at the peak of this cosine function. All right. So first thing, I just want to find out what is the period. So I also know that omega prime here is equal to omega squared minus r over 2L squared. And further, that omega is, like we've had already, that's 1 over root LC. So I need to find out what omega prime is, because that's my angular frequency of this circuit. And then from that I can find the frequency and I can find the period. So let's just calculate what omega prime is. It's going to equal to 1 over LC minus r over 2L squared. I have all these values, so that's going to be 1 over 12 times 3.2 times 10 to the minus 6. That's 1 over LC minus R. Let's see, R is 7.2 ohms divided by 2L. And L was 12 henries. Right, so that gives me my angular frequency of the circuit, and I find that to be 161.4. It's in radians per second. However, I really need to know the period, because I'm looking for certain time intervals of the period. I also know that omega prime is equal to 2 pi f. Actually, to keep in I'll have this prime. Remember, back when we derived this, there was a difference between omega and omega prime, but omega prime is still the angular frequency of the circuit. So I can solve this for f. That's going to be 161.4 over 2 pi. And I get the frequency. And actually, I don't know this value. It is what it is. I also want to know t. That's really what I want to know is, which is 1 over the frequency. So that's going to be 2 pi over 161.4. That's really the number that I want to know, and that number is equal to 0.039 seconds. This is the period of the oscillation that occurs in this RLC damped circuit, these damped oscillations. Okay, so now I'm ready to calculate my charge, because I want to know what is the charge after 5 time intervals, after 5t. What is Q equal to? Q equals what after 5t? And so I just say Q is equal to 6.2 microcoulombs. That's my maximum charge times e to the minus RT over 2L. R is 7.2 ohms. T is going to be 5 times 0.039 seconds over, was it 2L? Oops. Sorry about that. 2 times, I think this was 12 henries. Yeah. Okay, so that's the exponential all to that e to this value. Let me make that more clear. So this is e raised to that power. Then I can calculate that charge. Remember that cosine function at t equal 5 at the time of 5 periods is equal to 1. So I'm just going to leave that out because it's equal to 1. It doesn't affect my answer. And I find 5.85 microcoulombs. I do the same thing for 10t and 100t. I'll just give you the numbers, but it's exactly the same, except you're going to change this to a 10 now. And here I get a charge equal to 5.52 microcoulombs. And finally at 100t, I get 1.92 microcoulombs. So remember this charge, I'll very likely ask you to plot this, by the way, just to sketch it out. This charge gradually gets smaller and smaller. It follows that exponential curve, and it oscillates back and forth, but the maximum gets smaller and smaller because of that exponential function within the charge expression. All right, so that's number 7. Number 8, a 50 ohm resistor connected with a AC power source. The amplitude of the EMF is 30 volts. What is the amplitude of alternating current if the frequency is 1 kilohertz or 8 kilohertz? Okay, well this is a very simple question because actually the current in a resistor is not affected by the frequency. So I is just simply E over R. So that's going to be 30 volts over 50 ohms or 0.6 amps. And that's regardless of the frequency, either 1 kilohertz or 8 kilohertz. Now, however, this would be a circuit that would look like this. However, if I had a circuit that looked like this, where instead I had a capacitor, this is not true. My current here is equal to E over the capacitive impedance, or the capacitive reactance, excuse me. The capacitive reactance, remember, is akin to our resistance, but instead of not being dependent upon the frequency, it is. The capacitive reactance is equal to 1 over omega d times C. So this then would be dependent upon the frequency. The higher the frequency, the higher the current that you would get in this circuit. And similarly, if I had a circuit that had an inductor like this, the current here is equal to the EMF divided by the inductive reactance, XL, but XL is equal to omega DL. So this is equal to the EMF divided by omega DL. So if omega increases, this current will go up. When omega increases here, this current goes up, and I misspoke before. When omega increases here, this current goes down, and with the resistor, when omega increases, this current remains the same. It's unaffected by the frequency of your EMF generator. And we'll do 9, and actually on number 9, we're going to not do part C, so you can just forget about part C. It was a little more complicated than I thought. Okay, so here I have this AC power supply, and it's connected to an inductor. and I want to know what is the maximum value of the current. Well, this is just like the problem we did before. I is equal to EM over the reactance of the inductor, the inductive reactance. So that is going to be equal to 25 volts. Remember, this XL is equal to omega DL, so that's going to be 377 radians per second times 12.7 henries. And that gives me the maximum current, which is 0.00522 amps. So that's part A. And I just use this idea. I remember XL is equal to omega DL. Now, when the current is at a maximum, what is the EMF of the generator? Okay, well, this is a little more complicated. When the current is max, its maximum value, that means that its derivative is 0. Because look, if we're looking at a plot of current versus time, I'm not going to worry about the phase shift, but if I just plot current versus time, the current is at its max here, and the derivative of this function at this point is equal to 0. So when it's at its max, the derivative of the current is 0. That's important because the EMF of the inductor is equal to di dt. And so if the derivative of the current function is 0, that means there's no EMF of the inductor. So that means that EL is equal to 0 volts. Now, however, EL and the EMF are 90 degrees out of phase. All right, so if I were to plot the phasor diagram, let's say this is EL over here. It's at 0. That means that E will be up there. It'll be at its maximum value because the separation between these is 90 degrees. So the generator then, at this point, when the current is at its max, when the current is at its maximum, the EMF of the generator is going to equal 25 volts.